model for a very high Reynolds number bound there. I'll show you some of the trends that you can extract, some of the issues involved with taking data there. And I'll try and give you a very rough overview of the planetary bound layer in general, but that's not what I'm going to focus on now. I heard yesterday that a few of you are working in specifically that area, so you probably know way more than I do about the broader bound layer. I'm going to focus on the surface layer. So I'm Beverly McKeon from Caltech. What you see here is the experimental setup that I worked on a few years back, and I'll go into some detail about what you might want to consider when you do experiments in the surface layer, what we measured, what the results show us, and particularly what the limitations are. So you have this wonderful large laboratory, if you like, outside the window. I know there'll be no demonstrations this morning, but obviously there are things you need to take into consideration when you try and work in the surface layer instead of in a field campaign instead of in a laboratory in a nice clean environment. So, an outline. Why would one go and do this? The experiments are not simple. As I said, there are some limitations. What is the connection between the planetary bound layer, the surface layer, and some of the wonderful facilities that we'll see here, I think this afternoon, some of the other ways some of the simulation results that you get. So I'll go through the atmospheric bound layer very briefly, talk about working in the surface layer, some experimental concerns, then talk about the near neutral. By neutral I mean thermally neutral, so this is obviously one of the biggest constraints you have working in the surface layer. There are thermal effects, buoyancy effects that you need to account for and if you're careful. So the near thermally neutral atmospheric surface layer is a model for a canonical turbulent bound layer. And then show you some results and really try to identify what sort of questions you can realistically tackle in the surface layer, what sort of accuracy you're going to get, and why it's an important facility to use. Okay, so Philip talked yesterday about a range of Reynolds number results. Obviously in the surface layer you get a very high Reynolds number, so you can see up at the top here I put some sample Reynolds numbers. So on the left there is a transcontinental natural gas pipeline, runs across the Yamal-Europe pipeline, runs across the northeastern part of Europe. And industrial pipes, the Reynolds number based on the diameter of the pipe and the bulk profile, or the mean profile, order of 10 to the 7. D plus, so this will be RE tau for the pipe using the pipe diameter, so RE D plus. D plus will be the pipe diameter times the friction velocity or kinematic velocity, and then delta plus relative like yesterday for the bound layer. It's just some measure of the bound layer thickness. It will be, you'll see that that's another question we have to answer in the surface layer, but just the outer length scale for the bound layer thickness. So D plus in the pipe up to about 10 to the 5 of that order for the largest pipes. Boeing 777 on the right there, Reynolds number based on X, order of 10 to the 8. 777 wing, 10 to the 7. What's the REX in the surface layer? Where's the origin of the planetary bound? Okay, so that's the first question. We don't know the answer to that. Delta plus is of the order of 10 to the 6. And RE theta is about, depending on the conditions, about 5 times 10 to the 6. So remember yesterday the simulations were getting up to 4,000, I think was the maximum. So this shows you why one might want to work in the surface layer, just because you get that many orders of magnitude difference. And you're getting up to something that's going to be similar to these practical considerations in terms of the Reynolds number. So I would say that the high Reynolds number bound layer, surface layer, is a fundamentally important flow. You can study the behavior of very high Reynolds number all around the flows. And I think Philip talked a little bit yesterday about the idea of something like universality, meaning that it doesn't really matter too much about the particular flow you're in if you're very close to the wall. Now, you'll see as the workshop opens forth, and probably the workshop goes on, there are some obvious differences between flows, although it seems this to be emerging. But for now, let's say that there's certainly something that you can tell across flows very close to the wall. So we will use the near neutrally stable atmospheric surface layer as a model for a canonical Reynolds number, high Reynolds number boundary layer, and we like to say, or at least I like to say, that surface layer is the highest Reynolds number terrestrial available facility that you have. So if you start to think about a much higher Reynolds number, you start to talk about intergalactic distances. And I'm perusing from Melbourne, looking in next week to actually calculate some of this. And so that yeah, you know, if you try to get much higher a Reynolds number than this, you're talking about phenomenally large boundary layer thicknesses. So just a brief overview, experimental pros and cons. Why, again, is it useful to go to very high Reynolds number? Or why is it useful to go to high Reynolds number in the surface layer? This is a very important point. Usually as the Reynolds number goes up, if you look at delta plus being 10 to the 6th, you can think of that as a ratio between the larger scale of the flow, so the boundary layer thickness, and the smaller scale of the flow, so the viscous length scale. And unless you make, to get the delta plus of 10 to the 6th, unless you make delta very big, the viscous length scale is going to necessarily be very small, right, by a factor of a million. So if you do something like this, or try to get something like this in a laboratory flow, your viscous length scale is going to be so very small, it's going to be very hard to fully resolve that full spatial, possibly even temporal resolution as well. So the surface layer is a unique facility in the sense that this delta 99, well, delta surface layer is of the order of 100 meters in the facility, the site that I'm going to show you. Okay, so obviously that's not something that's really very realistic in a laboratory flow. So that means then that the viscous length scale is it's measurable. So the big problem, though, is going to be that it's not a stationary flow. You can't turn your wind tunnel on, set up your equipment, wind tunnel, everything, all the conditions are nice and settled, come back, do a few measurements, look at your data, say, oh, there are 50 points, or you traverse your probe. You can't do that. There's a finite time during which the flow will be stationary in the sense of wind speed, wind direction, thermal conditions, flies, bugs, birds, all these sorts of things. Okay? So you have to take a different approach to measuring things in the surface layer. Question?
What does that mean with near neutrally stable?
So we're going to come to that, but I mentioned at the beginning that there's a thermal condition in the surface layer. So the surface layer during the day has very different conditions than during the night. So it's basically a balance between mechanical forces and buoyancy. We'll come directly to that, and I'll show you what the planetary boundary layer looks like during day and night. So in order to reproduce the sort of conditions you see in the wind tunnel, you want the flow to be driven by mechanical shear, driven by the wind, not to have these buoyancy effects, or at least to minimize the effect of buoyancy. So I'll deal with this specifically in a moment. It's a very important point. But when I say near neutral or near neutrally stable, I'm going to be referring to thermal conditions. Okay, so who else studies the surface layer? Obviously, people like me who are interested in turbulent boundary layers are not the only people who are interested. A range of folks who look at this. Micrometeorologists looking at wind flow close to the ground. Meteorologists, weather, clouds, all sorts of aspects that you see up here. Aeronautical meteorology, what are the conditions going to be like for aircraft or flying? Predictive weather, agricultural meteorology, then on a bigger scale, climate analysis. How does one understand fluxes, clouds, gaseous exchange, these sorts of things. And global circulation. So GCM's global circulation models used to account for the effect of the boundaries. I'm going to focus on the near thermally neutral period, but people also consider the convective and the stably stratified flow regimes. And I'll come back to exactly what I mean by that in a moment. Urban planners, environmental engineers, many reasons to study this. And all of these groups ask different questions. So something I'm going to focus on, what kind of questions can we genuinely answer related to a turbulent boundary layer, and what kind of measurements you need to make to do that, because obviously there's a wealth of data on the surface layer some of which is suitable to use for our purposes, some of which is really targeted at different questions. So here we are. One of your references is an annual review paper by Wingard. That's really where you're going to see a lot of information about the planetary boundary layer, and in particular the convectively driven and stably stratified solar. So this is a figure from Wingard, and it shows the variation of the structure of a typical layer, a typical section of the planetary boundary layer with time. So it's indicated sunrise and sunset, so this is daytime and this is nighttime. You can see the surface layer he outlines here, and I'll go through the specific properties of the surface layer in a moment. You can see that there are regions above the surface layer. The surface layer is somewhere between 100 and 300 meters in height, and I'll show you that at the site I worked at, that's a reasonable estimate. And somewhere around sunrise and sunset are these near thermally neutral periods I was describing. So, what do we know about the planetary boundary layer? We consider it to be an incompressible flow. There's a huge range of scales. So, if you look at the full planetary boundary layer, you can see that the upper scale here is of the order of 1 to 2 kilometers, and then of course the atmospheric stuff above that. Coriolis force, the rotation of the Earth, is important, but in general, not in the surface layer, not that close to the Earth. And the exact importance of the Coriolis force as you go away from the surface will depend on where you are on the globe. So depending on where you are on this particular figure, there'll be different relative importance of mechanical shear and thermal effects on turbulence in the atmosphere. Now, obviously one of the issues associated with the planetary boundary layer is boundary conditions in general, but let me focus on the top boundary condition for right now. If we're going to look at the surface layer here, obviously what you have above it is not just a nice free stream of potential flow, as was discussed yesterday. So that's one of the problems associated with working in the surface layer. What is the importance of that upper boundary condition, and how does that permeate, or does it permeate into the surface layer? Heat transfer can affect this particular stratification here, and that could involve clouds, could involve entrainment of less dense air from above. So you have to be very careful about exactly what flows you're looking at. And of course, it's very difficult to measure that top boundary condition as well as what's going on very close to the wall. So you'll see in some of the measurements I show you that some of the properties are inferred from previous measurements as being typical of a site. The site that I'll show you, this is certainly true. So there are these things like delta, the height of the surface layer has been measured many years in a row, and within a certain error bar you can say that at this time of year there is approximately 50 to 100 meters. I would draw your attention to the fact that we're in meteorological units now, so distance from the wall is Z, yesterday it was Y. It's just one of those things. I may mix them up in between, but I'll try my best to stick to Z in the wall normal direction. So let's focus on the surface layer. You can see that the surface layer grows from sunrise, sunset, or from the transition between a convectively driven flow and a stably stratified flow. And it's about the bottom, say, 10% of the planetary boundary layer. Its depth varies with the diurnal cycle, and just as in the lower Reynolds number boundary layer, we'll see that its properties are, the fluxes are reasonably constant. There's a large constant stress region that will help us when we come to try and understand the skin friction in this one. Obviously that's going to be pretty hard to measure. So, near neutral or neutral, again, we're saying that the flow is a mechanical shear-driven flow. So we're going to say that in this particular regime, the effects of buoyancy are minimized. So let's take a look at what's going on now outside of these near neutral periods. And the near neutral doesn't exactly coincide with sunrise and sunset. So those are useful guides as to when you should be going out and measuring the field. I'll come back to it. There is a different case somewhere in the globe, but at this particular test site, which is in the western US, sometime around sunset and sunrise are the near neutral periods. Okay, so the stable boundary there. So, for example, during nighttime, under clear skies. So again, remember that upper boundary condition can affect what's going on. The turbulence production is only from the mean wind shear. The surface is warmer than the atmosphere, so there's radiative cooling of the surface, and this should say entrainment of less dense air from above. So there's a thermally stable flow. And this leads to a positive vertical gradient of potential temperature. I'll come back to that in what I mean by potential temperature, but for now, just keep temperature in mind. And a buoyancy force that counters any vertical displacement. So it's a stable, thermally stable flow. So the only eddies, turbulent eddies you'll see there, will be ones that have an inertial force large enough to overcome this damping of vertical displacement. So you can take a look at what that would be, and if you balance an inertial force, so Q squared on L, with a buoyant force, so we're in a Boussinesque approximation, so beta here is the gravity force divided by gravitational acceleration divided by the temperature, and theta 3 is the gradient of temperature in the wall normal direction. So if you were to balance the two forces, so beta, theta 3 times L would be the buoyant force, Q squared on L would be the inertial force, and if you work out what size of eddy is required to balance those two forces, you can see that you get this length scale here. So there's a limitation on what sort of turbulent eddies you see in a thermally stable boundary. The other thing to notice here is the general form, large rolls of cells, roll cells, if you like, in the surface layer. This line here is the variation of temperature, and this is an outline of the velocity profile. So not too much variation in the normal direction. So that's the stable boundary there. The convective boundary there. So this is a common daytime state over land, also over the sea, and you can see some large differences here. So this is driven by the surface temperature flux. You can see a different structure. So before we had just one dominant region of the order of a kilometer in height. Here we have three regions, so a surface layer region, a mixed layer, and then an interfacial layer between what's going on closer to the ground and what's going on further up into the atmosphere. So in this flow, Coriolis force, turbulent Coriolis force, is usually negligible. Surface heating and evaporation drives this convective layer. So mean wind shear may play a role, but it's not as important as this convective effect. So note that the scale of this first convective layer is smaller, about 200 meters. It's a larger, qualitatively larger shear close to the ground, and a profile in the temperature that's a little different from the stably stratified flow. So as I said, there's plenty more detail on this in WinGuide. This is the sort of radio that's of interest to you. Question, what's thermally neutral? How do we quantify the effect of buoyancy? So we could write down the turbulent kinetic energy equation for a horizontally homogeneous flow. And it would look something like this. And I'm using this virtual potential temperature, so it's theta V here. So the virtual potential temperature is given here. So we treat moist air as a perfect gas with the gas constant of dry air, but the virtual temperature which the dry air would have to achieve the actual observed density at the actual pressure, and that's TV, T virtual, or theta V. I'll use both of those together. I'm sorry, TV. So then theta V brings the air to standard temperature and pressure radioactivity. So this is the definition of theta V. And if the gradient of theta V in the wall normal direction is less than 0, there's a production of turbulent kinetic energy, and vice versa. So the most important point to make here is that it's very rare, or I don't know whether it's entirely possible to see more than momentarily a truly thermally neutral flow in which the buoyancy effect is not important for the entire surface layer. So I'll show you some results showing how the effects of buoyancy vary as you move away from the surface. And this is one of the effects that we'll have to consider when we start to interpret some of the results from the surface layer. And then the last point is, particularly where we were measuring the humidity is very low, so our assumption that we're treating moist air as a perfect gas and the gas constant of dry air is very good. So theta V is very close to TV and very close to your measured temperature. Okay, so let's see how exactly we're going to quantify this buoyancy effect. And a useful place, or useful location to understand would be the height from the wall at which the production associated with the buoyancy term, production of kinetic energy, and the production due to shear are equal. So we certainly want to be far away from that. Okay, that's when the effects are equal. We want to be in a regime where the flow is shear dominated. So if we were to write down the balance between the production from wind shear, the dUTC, so this is the production term that you saw yesterday in the canonical flow, and the production from buoyancy here, so W prime is the fluctuating term in the normal direction, and theta V is the virtual temperature, the bar is the time average here. You would have this expression. So we will define L as the height, distance from the wall at which these terms are equal. And this is known as the Monin-Overcroft length. So L, capital L, here. And we've talked about a constant stress regime. So if you were to, homework problem, see if you can get to the Monin-Overcroft length. We can talk about that later. But anyway, to get from here to here, you need to make some certain assumptions about the shear stress. So L, U tau, friction velocity, you saw that before. Kappa is the von Karman constant in the log norm. A hint, by the way, for the homework problem. And then here's the terms that were on the right-hand side. So this is the height, the Monin-Overcroft length, was interpreted as the height at which the mechanical shear and the buoyancy forces are equal. So, as I mentioned, you want to be far away from that if you want to be in a regime that's dominated by mechanical shear. So we want the magnitude of the height at which we're measuring divided by the Monin-Overcroft length to be small. Now, it could be of either sign, depending on whether the flow is stable or unstable, but we certainly want to be a long way from that. So a typical condition proposed by Hofstrom is that Z on L is much less than 0.1, or less than 0.1. Turns out that even when it's 0.1, you can still see some pretty strong buoyancy effects. So Bresser et al. Proposing it to be much less than 0.0. But again, it depends what kind of question you want to ask. If you're looking for trends, long sample times, you could probably get away with this condition. If you're really trying to make some direct comparisons between what you find in the surface layer and the laboratory found layer results, in which this is of course essentially 0, then you need to be very strict on that condition. So what we're saying here is Z on L is much less than 1, or very close to 0, we're saying that L is effectively infinite, so the height at which the buoyancy and the shear effects are equal is very, very long way from the surface. So all the way from close to the edge of the surface layer all the way down to the wall is shear driven, just as you would see in a controlled wind tunnel experiment.
What's the actual order of L in order of L in kilometers?
So it varies depending on the time of day and where you are. So it's going to change as these properties change. I'll show you some plots in a moment that show you the variation of Z on L as you go through the neutral transition. And you'll see that it's height dependent, as I mentioned to you. And you can actually get within this condition quite well, but over a very narrow window, and which will lead us into a number of problems associated with the surface layer. So I'll show you, might even be the next slide here. This is good, you're much more alert and awake than yesterday. So please keep asking questions. Okay, so it's not the next slide, we'll come back to that. So, equipment, how does one go about making measurements in the surface layer? Obviously, if the surface layer is of the order of 100 meters, it's kind of hard to get out to measure the edge of the boundary there. So you can do some remote measurements. So SODAR, acoustic radar, LiDAR, Doppler radar, all these things are ground-based. I think this is a SODAR, I'm not sure. So it's all sounding from the ground up, and you get a spatial volume average measurement. So if we focus on SODAR at the moment, SODAR stands for sound detection and ranging. And speed of sound, as you know, ground conditions is of the order of 340 meters per second. And if you have 3 antennae, you can get 3 velocity components wherever you're sounding up to. Another way to get up to the edge of the boundary layer is simply to float something up there. So you can use balloons, you can use telesons. So a teleson is just, balloon is lifted, teleson is tethered to the ground. Another thing that's quite often used in other fields is an aircraft, so actually making measurements from an aircraft flying through the surface layer. Obviously you can carry a lot of equipment, you can be quite mobile, and you can do some nice traversing, get some long samples. Problem, what's the plane actually doing, where are you measuring, how accurate can you hold your position, or know exactly where you are in the surface layer, or in the boundary layer. And of course, what does the aircraft actually do to the flow? So again, it depends on what questions you want to ask. So, etc. I could spend a long time on this, but I'll keep going. So that's general. Specific, so these are the techniques I'll talk about briefly, ones that have been used in the surface layer in the past 10 years, let's say, to answer some questions related to high Reynolds number boundary layers. So the first one, most people will have seen in high school. You see off buildings. Cup and vein anemometry. So here's the cup. So it's a shaft with 3 cups that catch the wind. The rate of rotation tells you something about the wind speed. So that's the very first measure of wind is strong, wind is not strong. Do I want to be measurements today or not? And then the vein here tells you the direction of the wind. It's a very crude visual. What's going on my probe's pointing in the right direction. And you'll see we actually use this for quite an important thing, important task in the measurements I'll talk about shortly. Sonic anemometer, shown here. Very useful device, works by the time of travel of a sonic pulse between 2 receivers. Okay. Typically these have a lower sample rate than some of the other techniques, but they're very commonly used and they're very robust. So you'll see in the literature many examples of sonic anemometer arrays being put out in the field, sort of left for months, data being fed back or recorded locally or transmitted back. So the benefit to the sonics is you can get 3-component velocity information. So you can see there are 3 may be perfectly fine for what you want to do, but I remind you that in the surface layer, the viscous scale was somewhere between 10 to the 3 and 10 to the minus 3 and 10 to the minus 6 meters. So if you think about what you're averaging over in viscosity material, it's quite high. So, depends what question you want to ask. Then, probably most people are familiar with constant temperature anemometry, hot wire anemometry. I'll show you some examples of single hot wire measurements. People have also done cross wire measurements in the surface layer. And then there are some amazing multi-wire probes capable of getting 3 components of velocity to vorticity as well. A drawback to these is you need to calibrate them. And of course that's much easier in a wind tunnel where again you have a nice long time where you can come up and calibrate the wires. Out in the surface layer, first of all, time is kind of short. You need to be close to the near neutral when you're calibrating. Second of all, you're out in the field, so you see a swarm of bugs coming towards your array of hot wires, you get very nervous. If you see some dust storms coming towards you, you can lose many wires in one go. So hot wires are pretty robust, and I'll tell you some stories later about how surprisingly robust they are in the surface layer. But you need to have a strong constitution in order to work with hot wires in the surface layer. I'll show you some flow visualization results, so you can introduce smoke or a tracer. In fact, sometimes the surface dust actually shows you quite clearly what's going on in the surface layer. You've probably seen this as you've looked out, certainly out where I live in Los Angeles. There's a kind of, you see dust devils spinning up, you see the dust spinning out, so you see nice looking turbulent structures developing in the dust spinning up. You can go a step further and say I'm actually going to either introduce a specific seed or use the natural seeding and take some particle image symmetry. So now we're really talking about taking expensive equipment out into the surface layer. Again, you have to be not a nervous person to do that kind of thing. And here's an example from some of Morris's work. I'll give you the full reference shortly. So these people introduced a fogging system mounted below the desert surface. So introduced seeding here, put their laser sheet, please give it a picture, initiated it from downstream, and then had two cameras for an extended field of view in this direction. So again, you take what you get in the surface layer, you can adjust the speed, wind speed or direction, and a little story about these experiments. There were 2 students out in the middle of the desert, and they had 2 weeks to get the data. Nothing for the first week. Wind even blew the wrong way. So they were all set up for the wind coming this way, the other way. Last but one day, they filled 3 hard drives with PIV information back up to my home, and it's the data that's reported with JFM paper. So it's just very different. That will stress to you, it's very different from the in the laboratory. You can also do surface pressure measurements. I won't spend too long on those here, but obviously that's something you can do very well. You can get to the ground, you can measure, you can bury sensors, and the results are really in surprising agreement with what you would expect. Very nice agreement with what one would expect from an extrapolation from laboratory. So, if I can stress one thing to you about measuring in the surface layer, well, I can stress 2 things. The first is there are many uncertainties. The trick of using surface layer data to augment what we know from the laboratory is to know the limitations of the data, to know there are large error bars. What I'll show you is even with those error bars, you'll see that the surface layer, because it's at such a high Reynolds number, gives us useful trend information. The second thing I would stress is you need to identify what question you want to ask. So you can certainly get large-scale, spatially average information a lot more simply than you can local, resolved information, but it depends what question you want to ask. So, the near-neutral atmospheric surface layer is the model for canonical ZPG, zero pressure gradient bound layer. I don't think I have many more absolutes, but failing the layer, shear is the dominant source generating the total kinetic energy. And this delta surface layer, a surface layer thickness, obviously from what I showed you before, there is a velocity profile that continues all the way through the boundary layer. The height of the surface layer is generally found from a minimum in the gradient of the horizontal velocity profile. So there is a profile associated with the near wall flow, and then it will change, and you can identify at least approximately what that boundary layer height is from the gradient from a telesonde or a radiosonde. Advantages, I mentioned that it's a very high Reynolds number, large physical and temporal scales, and it's free, as long as you can get out there. So disadvantages, we've gone through buoyancy effects, the upper boundary condition I talked about quite a bit. I haven't talked about the lower boundary condition, but I'll spend some time on that, so the wall boundary condition. And control, so the velocity and the direction of the wind and the temperature are something that you can't control. As I pointed out at the PID, you just take data, and then the way we did it was then analyze afterwards and see what was the good data and what really you couldn't use. Field campaigns are difficult, and I've ignored weather. Okay, so depending on where you are, you can have other scales of motion and other phases of fluid, so you might be radon, etc., etc. How are you doing? Do you want to break now, or should I keep going? Oh, you're good. All right, I'll keep going. So wall boundary condition.
Go on for 50 more minutes. Let's take 5 minutes break, and we have coffee at 10:30.
10:30. No, 9:30. 10:30. You said take a break after an hour.
Yeah, take a break like 5 minutes.
5 minutes after an hour. Okay.
Move around.
All right, but let me give you a warning here. If you don't speak up, I'll keep going. So, surface roughness. Jonathan will spend a whole lecture this afternoon telling you about surface roughness, so I'm just going to give you some of the things that are relevant to working in the surface layer. So you saw yesterday the logarithmic law written in terms of u plus equal to 1 on carbon constant times the log of z plus y plus it was yesterday, now z plus plus a constant. So typically in the meteorological sense, you can rewrite that in terms of an aerodynamic roughness length, Z naught. Okay? So it's just a reformulation of what you saw yesterday. So Z naught we call the aerodynamic roughness length, and if you work this through, mini homework problem if you're interested, you will see that Z naught is the location where a log law extrapolated to 0, where the log law reaches 0 velocity. So it's just another way of writing this, and Z naught gives you some indication of the roughness of the surface that you're working with. So the site that I'll show you, SL test, and I'll also tell you what that stands for, up on the salt flats in Utah in the US, has roughness heights. So the physical dimension, the average dimension of the roughness, is of order 1 to 5 millimeters. And that would correspond to a Z naught of about 10 to the 5 meters. Now, is roughness constant in the surface layer at a particular site? Depends what you're measuring over, but you can imagine, first of all, if you're out in the desert, so this site I'm talking about is out on the salt flat, so it's a salt playa. And you can actually only go out around in the spring, because if you go out any earlier, it's mud, so all your equipment sinks and you sink. If you go out too late, the surface has dried and it's become dusty, and it's cracked, and it's very rough, so you're at this end of that roughness range, or even further out, it can be very rough. So probably not on a day-to-day, or not on an intraday scale, or an out-to-out scale, but certainly on a week-to-week scale, the roughness height can change quite dramatically on the same site. So, for example, I'll show you some data from here, and if you had a prolonged measurement campaign and you timed it really well, you could actually go from a hydrodynamically smooth regime to something that was fully rough, and you'll hear more about what I mean by fully rough this afternoon. you're measuring out over pasture, over grassland, for example, the grass will grow, that will change your canopy. There may even be animals grazing. How do you classify that as a grass? Some data sets that there are no cows in the field. Okay, so the bottom wall band condition is something again you need to monitor really carefully. So here are some examples. This is a book, Garrett. It's also on your reference list. That gives you an example of this aerodynamic roughness type for different types of roughness. And I'm not going to go into too much detail about here, but you'll see that they're classified by the canopy height. So if you have grass or trees, what's the height of the stuff that's growing from the surface, and Z0, aerodynamic roughness length, and there's another column, doesn't have two, well, here you can see some of the data here, and that was D. So D would be the level of the action of the drag on the roughness element. So less important, but let's take a look at Z0. So grass, thick, thin, and sparse. Now, I'm not an expert, but I'll probably have trouble distinguishing between thin grass and sparse grass. But you can see that Z0 here changes from the lowest is about 1 millimeter up to about 5 centimeters. Okay. Crops. There's a famous experiment over the corn. Vegetation, woodland, very vivid, forests. So you can see there's a wide range from 1 millimeter up to several meters on this Z0. Now, obviously, if you're over a forest, you have some other things to worry about in terms of what's going on inside the canopy, and I think there's at least a couple of people working on canopy flows when we went through it yesterday. So, what we're talking about for the experiments I'll show you shortly are very small K, very small Z0, but I'll show you that the effective roughness still needs to be considered. So, skin friction. In all the introduction yesterday, you saw that the scaling with U-tau, friction velocity, is very important. Skin friction is very important. It's always an issue in boundary layers, how you get that. It's experimentally. In an internal flow, in a channel or a pipe, you can always get it from the pressure drop, for a fully developed flow. In the boundary layer, obviously you'd like to make a direct measurement, so you know exactly what U-tau is locally. There are also indirect ways to get the shear stress. And out in the surface layer, Meredith Metzger, who was my co-conspirator, collaborator on the data experiments I'll show you shortly, for her PhD actually did a comparison between these images going through the evening transition through near neutrally stable. So she measured the direct shear, or she performed a direct measurement of the shear stress of the surface using a drag plate. So this is the site, and you'll notice one very important thing about this: there's nothing there. Okay? Very flat, no vegetation, no hills, nothing like that. But here's a surface-mounted drag plate. You can see the disc here, and that's embedded flush in the desert floor. Then one indirect measurement, of course, is to get the velocity gradient close to the floor. Now, in a laboratory boundary layer, it's pretty hard to do that to get close enough that you can get into, say, the viscous sublayer and see the linear region, or even a little bit further from that, from the wall. In the surface layer, you can do that quite well. And then the other way, other indirect way, is that in the region of constant shear stress, if you measure the shear stress, you can back out what the velocity must be. So here are some data. You can see this is over a couple of hours. The black and the grey here are from sonic anemometers, so they're measuring the constant stress they're measuring the Reynolds stress, and then assuming it's a constant shear stress from the wall, backing out U-tau. Then the red is the hot wire measurement, so this is the second point here that I'm using the velocity gradient near the wall to get the shear stress. And then blue is the direct measurement of the drag plate. So the first thing you see is that they're pretty good agreement. Okay, there are error bars, but you can see that particularly between these dashed lines, which are the indications of where the near thermal neutral period things go a little bit haywire when you get out of that period, but what fails? Of these three measurements, there's an assumption built into one associated with thermal stability. This is an assumption based on the effective buoyancy being minimized. So once you get outside of these dashed lines, you wouldn't necessarily expect to all through you. Another thing you can pick out from here is that these dashed lines represent the Z on L, so the ratio of the height of the sonic anemometer to the motor and Overkopf length being within 0.1, plus or minus 0.1, and you can see that that gives you just under an hour. So you can understand if we were to use a sharper criterion, so less than or equal to 0.01, then you have really quite a short transition through near neutral. Okay, stability. This is the answer to your question. Okay. What I'm showing you here is the magnitude of the distance from the wall to the motor Overkopf length versus time on one day that we took data out at this site. And there are 4 lines, and these are sonic anemometers mounted at different heights from the wall. So this direction is increasing height from the wall. And you see what I was showing you before, that there's a small region in which Z over L is essentially 0. So L is approximately, L goes to infinity, L is very large, so everything that we're measuring is shear driven. And if you zoom in on this region, you see this type of thing. So if we were within a Z on L of 0.1, that's what these dashed lines denote for the first 2 sonic anemometers. And the sonics are, I think it's 1, 3, and 5 meters from the wall. I'm not sure. I'll check it right. I forget what the first one is. I'll check the actual height. But you can see you can draw a line across here, and then mark in where you obey that Z on L less than 0.1 condition. And if you were to be much stricter and say Z on L less than 0.01, it would be in here. Now there's some measurement noise on here, but if you average, you'll see that there is a region where there's definitely a minimal effect of stratification or buoyancy. Now the other way to identify what's going on here is to look at the spectrum of heat flux. Okay, so remember, depending on whether if you were to be outside near thermally neutral, there would be a heat flux either to or from the wall. So if you look at the mean theta prime, theta fluctuation, and W prime, so theta prime, W prime, you look at the spectrum, you would see either side of near thermally neutral, you see a large positive covariance, or not large, you see a distinct positive or a distinct negative covariance. And in this region that we really identify as near thermally neutral, there's essentially 0 heat flux. Okay? So we really are in a mechanically shear-driven regime. The other thing that's quite interesting is once you get close to the transition, you see something that's close to linear with time either side. So, important thing is if you draw this Z on L less than plus or minus 0.1, depends on your measurement domain, first of all. So if you're very far from the wall, you're going to have a much smaller time domain than if you look at this one here. This one you could draw it right out to here. This one you have to come right up to this time. But it depends, again, what question you're asking, where you're measuring. Is that asking you?
Actually, the other question, I mean, this 15 minutes is enough to measure some sort of
No, and that's the big problem. Okay, so you can see from the stability plot that there's a very clear regime, time period in which you want to do your measurements. Right? I mean, it's very clear here. But this is a very good point. Can you get converged statistics, converged data based on this period here, this tired. Okay, so let's take a 5-minute break. Associated with that is if you take a very long sample, your probes are fixed in physical height, but if the wind speed and or direction are changing, and if the friction velocity is changing, where the probe is located in non-dimensional space, so in viscous units, for example, can be changing. And this is a problem that we specifically tried to address in our experiments by taking quite short samples, so at least we knew where the probes were in viscous units, but at the expense of not having converged statistics. So, I touched on this in the last slide. How do you separate turbulence that I want to measure from everything else that's going on in the atmospheric boundary layer? And we talked a little bit about three-dimensional turbulence, non-stationarity. There's a continuous spectrum of atmospheric motion. And we really want to identify the TKE production associated with the mean wind shear and separate out things associated with mountain terrain, such as roughness, clouds, buoyancy, anything that's not just the mean wind shear. So statistical separation of the turbulence from everything else really requires a gap in the spectrum. Otherwise, if you have a continuous spectrum, you're really making a subjective judgment about what is the turbulence and what is the stuff that you're multiplied power spectrum of the streamwise and more normal velocity fluctuations. You can see here this problem of convergence. These are very noisy spectra, but this would be turbulence, so from about 10 to the minus 2 hertz up to beyond 10 hertz. I'm showing you a sample here because I'm focusing down here, but you can see that there's essentially a minimum here, and then you start to pick up again beyond that. So if you were to run for a longer sample, you would see something else going on out here. So this is known as the Penofsky gap, and is used to separate turbulence from other atmospheric motions. And you can also see it in the covariance of the Reynolds stresses, so covariance of the velocities. So I talked a little bit about knowing where your probes are in non-dimensional space. Here is the output from the cup and vein anemometer in the experiment that we performed. So you've got time on the x-axis here, and the blue record is the wind speed. This is averaged over 1 minute sliding window at 2 meters from the surface. And then red is the wind direction. Dashed lines again correspond to the z on L less than plus or minus 0.1. So you see something associated with this site, at least, that's quite interesting. So during the daytime, there's a noisy signal, but it doesn't vary too much in either speed or direction. As soon as you hit the near neutral period, you see an almost linear trend in the wind direction. So the wind is rotating, so it's going coming from the north, and it's rotating out this way. And the wind speed also drops. The mean wind speed at this measurement height. So I don't have a similar plot showing you the friction velocity, but if the friction velocity is changing also, and there's reason to believe that something's happening if the mean velocity is changing, it's like changing the free stream velocity, then your viscous unit is also changing with time. So your fixed height probes are drifting in Z class. So it's a pretty tough problem if you really want to know something that's going on, or what's going on in different regions associated with the schematic that Philip showed you, where he showed you the viscous sublayer, the buffer layer, the logarithmic layer, and the outer region. So the other thing I should say here is that the neutral period is not known a priori, so it varies day to day. So we would typically take data for 3 or 4 hours, and then you could get a running estimate from the sonic anemometers, but it's very hard to do that instantaneously and say, you know, this is when I need to be running, and then have everything ready to go. So that's also a difference from being in the laboratory. So another consideration, the averaging times versus the sample frequency. So the sonic anemometers that I showed you before typically have quite a low sampling frequency. So the one unit that I'll show you a figure of shortly, I promise you we'll get to these experiments in a couple of slides to see what just over the page for that. So there's CSAT-3, the Camel Scientific device that was used also in this measurement campaign. Samples at 20 hertz. So once you put the Nyquist criterion in, you can resolve 10 hertz with a 10 hertz signal. I mentioned to you also that there's at least 10 centimeters cubed, 10 centimeters all cubed as a measurement volume. But you can get a long temporal record free velocity components from the sonic anemometer. The question is whether 20 hertz is fast enough to resolve the smaller scales of turbulence, the highest frequency. So the constant temperature anemometry can give you higher sampling frequencies, of course, much smaller measurement volumes, but storing all that data can be quite tough. So typically you would have a shorter sample period, depending on, again, what you're trying to sample, what you're trying to record. So here's a plot from Kunkel and Marusic, also your reference list, and this is the pre-multiplied, just as Philip showed you yesterday, this is f phi of f, or the streamwise velocity component. Here's the frequency. And the grey is the sonic anemometer record. Sonic anemometer record. And the black line here is the Nyquist criterion for the sonics. So you can see that with the long record length and the sonic anemometers, you can resolve a lot of the spectrum, but not all of it. Now with the hot wires, you could resolve all of the spectrum. I actually don't know which one of those two records I would say was noisier, so that's more to do with the duration of the near neutral period. But you can see that particularly in the more normal component, you do quite well with the sonic. Stress again, convergence is a major issue, and I talked about the non-conventional protocol. So I would say the other thing about sonics is there's a certain measurement volume you can resolve, but it's also a big piece of equipment. So there's also a finite number of these you can stack. There's a finite spatial resolution you can get in terms of just putting these things on top of each other and the effect they have on the flow. Okay, we're getting to the experiments. Notable previous studies, several in Sweden. People have worked in the Arctic and the Antarctic. Do you want to know why? Why would you want to work Arctic or Antarctic?
No corrosion.
Flat? No roughness? Other one?
No corrosion.
Coriolis? Any other one? Is it nice and warm?
No.
No. So your thermal conditions are different. So actually your near neutral period is quite long. So that's another reason people want to go out there. People want to go out there. I don't know why they want to go out there. Minnesota, Kansas, some famous experiments with canopies in the US. And then the ones I'm going to talk about are Utah salt flats. And if you look at Google Earth, you can pick out where we actually work. So you can see it quite distinctly from, actually you can see it from space, that you can see here. This is where I live. This is where I went. And this is the test site. So as I mentioned before, it's a salt flyer, and the surface condition depends on when you go out there. This is the dry lake bed of Lake Bonneville. So this is the region where they do the land speed testing. So if you've ever seen that done, very, very flat, very, very long, nothing else there basically. So it's very good for experiments. So this measurement domain, if you like, is of the order of 240 kilometers in the northerly direction, north-south direction, about 50 kilometers at its minimum point across, and this is the measurement site that we use. So when the wind is coming from just off north, there's really nothing upstream for many, many tens, hundreds of kilometers. When the wind drifts around over here, you can see there are some topological features. They're quite a long way off, but it's still really an open question whether that's good data when the wind is coming from the north-northeast. This is actually double-way proving ground in the US. So it's where they test chemical weapons and all sorts of things. So it's a very exciting place to do tests because you get instructions like, if you see something odd by the side of the road, don't touch it. Particularly if it's green. Oh, okay. So, and then every so often, actually, this mountain here was a bombing target. So being engineers, every so often you'll see some fighters or bombers go over and everyone will stop and easy to continue. So let me go back to the experiment. So the important thing is that there's a very long, flat fetch coming in. And then the change in height is less than 1 meter for 13 kilometers upstream of the test site. Okay, so that's the large-scale variation. So it's very flat. And the small-scale variation I showed you already, the K, the mean small-scale roughness height is somewhere 1 to 5 millimeters. And it's a very well-calibrated site in that we know that during good measurement conditions, the wind is predominantly from the north. And I showed you what the transition looks like in terms of the angular change. But you can get good data this way. Here's a highway. So I was telling you about moving roughness elements, but this is a long way away. So that doesn't affect our measurements. There's a causeway across here, an access road. So I also was telling you about the PID measurement where the wind was coming the wrong way. So there's a road across here and some trailers. So you can't really measure when the wind comes from the south. But usually it comes from the north. So this site is an Army-owned ground. And Joe Plewicki, who was at the University of Utah, is now at the University of New Hampshire, was responsible for setting up the site. site, I'll show you a picture of it, it's essentially power run out in the middle of the desert and a couple of trailers so you can store your equipment. So there's really not a lot there, as you can see in these pictures. So here's the view to the west, nothing in the view to the north, and this is another picture across to the west. So we're getting now to the measurement campaign. So SL test, actually I didn't go through it in the last one, stands for Surface Layer Turbulence and Environmental Science Test Site. SL test. So this particular campaign was run in 2005, and there have been several before at this particular site, probably not quite on this scale. So this actually involved researchers from four countries and several groups. And you can see there are a few experiments here. So this is an array of sonic anemometers, and I'll show you some results. This was from the Melbourne group, so space over 30 meters at the same height. So then there's a 26-meter tower with sonics. You can see them on this tower. You can see it. This is a very different array here. So that's one experiment. That's actually me. Yeah. This is American Mexico. This was our experiment with hot wires. And this is a data card. It's very important. Everything has to be mobile. So the experiment that I'll talk about had 31 synchronously sampled single normal hot wires over a 5-meter tower. So there's a 4-inch rake here with 15 hot wires, all these wires are logarithmically spaced. So 1-meter tower with a further 8 hot wires, and then a 5-meter tower with another 8 hot wires. And that should add up to 31. So we lost a few along the way. There are many reasons why they might fail in this scenario, in this setup, but we got quite a lot of data with these 31 wires. And you can see that the 1-meter tower and the rake are mounted on a plate that's embedded into the surface. And that could actually be rotated depending on the direction of the wind. So could the tower be rotated. So everything was aligned to the dominant wind direction. So the measurement plane is at the same streamwise distance. You get a very small error as you start to rotate in just because you're not rotating about the same point, so you start to move the wires apart. I think you can see it. I think that's the cup and vane anemometer. This is the CTA anemometer on this tower. That's the data card. What you see here, we saw in another figure earlier on, that's a surface-mounted drag plate, which actually didn't function too well in this particular set of experiments, but some work has been done before and after with that. And this side of the photo, there were surface-mounted pressure transducers, so another altogether. I promised someone that reference. I won't get time to talk about that very much today. So, quite a large-scale experiment, and sonics, I said, are pretty robust. You can leave them out there. So this group got to set them up and take the data, see what was going on. Hot wires are too sensitive for that, so we had to put these up every day. We had to calibrate them, put them up every day, bring them down at night, recalibrate. So we were calibrating before and after and tracking the temperature change during the data period. Okay, so the stability plot. Everything I'll show you from now on actually obeys the strict stability criterion, so 0 now, much less than 0 1. And just to give you some sense for the numbers, at the highest hot wire, the mean velocity was the order of 5 meters per second. Delta was estimated to be, delta S was estimated to be somewhere between 50 and 100 meters. Delta plus was order of 10 to the 6, and for this particular set of experiments, C naught was between 0.2 and 1 millimeter. Synchronous measurements. Now, the synchronous nature of the measurements allowed us to ask certain questions, but it also presented us with a data recording issue, because that's a lot of data. So sampling at 5 kilohertz, that's a lot to sample, hold, and store. And as I mentioned, we were worried about where the probes were in non-dimensional space. So we actually took quite short samples. but lots of them. And gives you about 20 large eddy turnovers associated with this 5-meter velocity. So that's not really long enough to get converged statistics. Certainly you'd want to run longer than that if you were in a wind tunnel. But as I'll show you, you still get some useful trends from it. So we were able to use the sonic anemometer array to give us an estimate of the friction velocity. And as I mentioned, that was a sample at 20 hertz. So, why would we want to do this synchronous sampling? What I'm showing you here is the interpolated signal from the 31 hot wire from one of the 210 records. So here's time, and we put together the 31 signals and then interpolate between them. And what you see on the top is a local mean, so there's a sliding window of 1 minute applied to that. So it's not the true mean, obviously that would be a constant at each height, but it gives you some idea of a large scale velocity variation. And you can see some pretty interesting features. So you can see that all the way across the layer you get this low speed bulge, and then similarly you get a very high speed excursion that seems to penetrate all the way down to the wall on the large scale. What you see below is the local RMS based on this sliding window. And you see something else pretty interesting. So in general, when there's a high speed, large scale velocity excursion up here, you see that there's an increased activity at the small scale. So the RMS is showing you kind of the small scale activity. And reverse, when there's a low speed, there's not too much going on here. But you can see that this happens across a range of scales. Okay? So here's the big, these are two sort of big features. But you can see that even within this sample, when there's a kind of smaller scale local positive excursion, there's a little bit more activity here. So it gives you some sense of the nonlinear nature of turbulence. It gives you some sense of the correlations that happen and the scale of those in this very large, very high Reynolds number bound there. So I think this is a nice picture just to give you some sense of the value of taking synchronous measurements. I should also tell you that in the surface layer we talked about non-stationarity, so traversing is really not an option, because by the time you traverse the probe out, your conditions will probably have changed. So people have done this sort of thing before in the community. They haven't done it over the 5 meters that we looked at. So note that this is all dimensional, so this is time and distance from the water. So let's get into some more specifics. So the mean velocity. It's very easy to measure the mean velocity. I showed you large error bars on the friction velocity. So you can't really, and there are some exceptions to this, you can't really use the surface layer data to answer questions about the scaling of the mean velocity. You could have referred to some of these earlier about the exact form, whether it's a power law or a log law, or what the exact value is a constant set. You can sort of see whether the data agree with it, but you don't really have the accuracy with which to make a prediction. So here is a collection of data from the SL test site. And this is so log of the Z plus, this is from the wall, and U plus. And these lines here show you what the effect of roughness would be on the log wall. And you'll hear a lot more about that not too far away. So here is a combination of hot wire and sonic data from 2003. Here's some 2005 data. And here's some data where the flow was, the surface was approximately smooth. So you can see, same site, probably very closely the same dates during the year, but the weather conditions were sufficiently different that you get a range of roughness effects. Here's some data from the PID that I'll talk about a little later, Morris et al. And you can see that their data quite well agree with the log law. There's some variation here, but again, our sample times are quite short. So I think you could really say that the surface layer results support or agree with, or at least support a first order approximation of the log law. I mentioned that you could span a range of roughness. The uncertainty in U-town, non-stationarity, etc. Make these scaling arguments very difficult, and Hassan Naguib et al. Have estimated that to really make some of these scaling arguments, you need about a 0.1% accuracy in your measurement of skid friction. Now, obviously, we'll know where to get that in this sense. So behavior is generally logarithmic. Now, the effect of instability has been shown to have quite a strong effect on these constants, on the mean velocity scaling. So this is a study in the Arctic from Andreas et al., who took mean velocity measurements over a range of stability conditions. So here's our Z on L. So I don't know the whole thing again. Looking between minus 0.1 and 0.1. So you can see another reason here why one would want to use this very tight condition of Z over L between 0.01 plus or minus 0.01. So there's a lot of data here. This is sonic anemometers in the Shiva experiment, surface heat budget of the Arctic Ocean. And you can see a very strong trend even within that cloud of data points on the von Karman constant. So we've got the apparent von Karman constant, the apparent slope of the log law versus stratification versus Z on L. So the stratification affects the von Karman constant. You can correct for it, and these authors actually did that, so you can go into the paper if you're interested in that. But again, you need to be very, very careful with the thermal effects in the surface layer. Okay, so that was the mean velocity. So what do the streamwise and wall normal fluctuating components look like? This should give you another sense of why one might want to work in the surface layer. So here, Kunkel and Marusik are streamwise and wall normal spectra, and it's plotted in a particularly nice way because you've got the surface, the laboratory results here, these ones, and then the surface layer up here. So you can see you get a much wider range of scales associated with the surface layer. You can see a long extent, something that at least resembles the k to the minus 5/3, scaling. And the other trend you can look out here is that this is increasing distance from the wall, increasing Z plus. So Kunkel and Marusik measured a little bit further from the wall than we did, and you can see that if you look at these trends. So that's streamwise in log-log scale. Here's the wall normal component. And Philip introduced to you the span-wise scales. I'm going to spend some time talking about the various streamwise scales that become important. We've mentioned what was going on close to the wall. I'll show you something that you see very clearly as you go up in Reynolds numbers. You get the scale separation associated with increasing Reynolds number. But if you look at this plot, there's an obvious difference, and it's labeled here. There's something that may resemble at least a k to the minus 1 region. There's energy associated with low wave number that's absent in the wall normal component. So that makes physical sense. You think about the presence of the wall. You can have very long structures parallel to the wall, but the wall itself blocks everything that should be in the wall normal direction. This is the streamwise component, but this is the wall normal. And of course, if you integrate the spectra, you get the intensities. Here are the streamwise intensities, or a selection of them. Here is a comparison. They both have comparisons between the laboratory Reynolds numbers and the surface layer. So here are the laboratory scale Reynolds numbers, so increasing RE tau in this direction. And here are the surface layer results. So the first thing you notice, large error bars. Second thing you notice is that the surface layer results from our experiment don't follow this trend of an increasing peak with Reynolds number, and there's a deviation down here. So there's a clear influence of the effect of roughness on our results. So even with about a 0.5 to a 1 millimeter mean roughness length, that's quite a large Ks plus, so a mean sand grain roughness. And if you go back to the mean profile, you can see that our data are down here with a K plus of about 50.
What is the use of directional units here?
It's about 0.15, 0.1 and 0.15
0.1 and 0.4.
So there's an effective roughness close to the wall. And the estimate, again, I'm going to touch on it, but roughness is known to have a strong effect, at least within about 3 times that mean roughness height in plus units. And you can see that this dashed line shows the region that's affected by roughness height, and it's a little over 100, so KS plus 50 is reasonable for, I think. If you look at the Kunkel and Marusik results, they've got it in inner and in outer scaling, so using an estimate of the delta for the surface layer. They also show laboratory data, so RE count increasing here. These dashed lines are a prediction from something called the attached eddy hypothesis. I won't have time to go into that, but it's something that allows you to make at least well, you can see it's quite a good qualitative prediction of what the intensity should do at this very high Reynolds number. So here are their data points and their estimates of what delta plus was during these multiple runs. So order of 10 to the 6 for delta plus. You can see that the laboratory ones go up to about 10 to the 4 and delta plus. And then this plot is really, there are several that show this type of thing, but this really shows you the value of the surface layer. So what we're looking at here is the value of this peak. So the peak at Y plus, T plus is about 15. That is associated with the near wall cycle that we mentioned yesterday. As you increase Reynolds number, so we've gone back to RE data here. So here are the laboratory data. The open diamonds are associated with the review paper of thermal sensitivities. Bring together what was in the literature at that time. Then here are the results. These ones are the results from the surface. These ones are these laboratory results up here, and then these are the range of the surface layer results for that here. So even with the large error bars in both components, you can see that where you might have had trouble extrapolating a trend from this cloud of data, and remember that spatial resolution, measurement resolution problems are quite tough in the laboratory as your Reynolds number creeps up. You can see that this point out here shows you a trend, that this peak is increasing with Reynolds number. So that, take one thing, hopefully more things from this lecture, but the value of the surface layer is this increase, this 2 orders of magnitude difference in Reynolds number that really illuminates some of these trends. So the surface layer shows you that the near wall peak continues to grow with Reynolds number, and the attached eddy model would suggest that it's a logarithmic dependence, and that looks reasonable associated with that plot there. Now, there is a caveat here, which is that that trend is solely dependent on what you see in the surface layer. Okay? So there's really quite a pressing need to fill in this area with data that has smaller error bars, but maybe bigger than down here, just to confirm that trend. And that's sort of an issue in the community right now, is how you fill that in. And there are some experimental facilities that will push you up out here. More normal fluctuation, so this is streamlined from the top. Here's the more normal fluctuation. And again, even with the scatter, you can see a nice trend. So, streamlined spectrum. Philip showed you the pre-multiplied spectrum, and he showed you the composite. This sort of picture. So you saw this type of thing yesterday. So this is from the wall, and this is a composite plot where you take the pre-multiplied power spectrum and you stack the slices together. So it gives you a composite map of where the energy is concentrated in the band there. So if you look at a laboratory Reynolds number, which is a delta plus of close to 10 to the 4, it has this sort of shape, and this is a schematic of the results from Hutchins and Marusik. So close to the wall, with lambda x plus of about 1,000, you see the near wall peak activity here. At this Reynolds number, delta plus about 7,300, you start to see also something that scales, well, it has a longer wavelength, and it's further from the wall, and it's hypothesized, it's been shown that this scale is actually, this structure scales better with the outer length scale. So here, this peak is about lambda x plus 1,000, and depending on the flow you're in, this length is about 6 to 10 times the outer length scale. And because of that, at a low Reynolds number, these two sit very close to each other. And you need scale separation, so you need to go up in Reynolds number. You need lambda x on delta of 6 to be quite different from a lambda x plus of 1,000 in order to be able to distinguish these two things. So this happens a little bit later in the streamwise component than it does in the in the streamwise length scale than it does in the spanwise length scale. So that's what you would expect at a reasonable laboratory scale. You could make a similar plot from the surface layer results. And if you put the picture from the hot wire experiment I showed you, with a sonic rate and the Matheus Hutchins and Marusic interpretation of the sonic data, you can see something similar at least. So here's the energy concentrated with the near wall cycle. It's reduced because of the effect of roughness. And then there's something else going on out here. Now you can see here clearly the effect of the lack of convergence at a very noisy spectrum. But there's an overlap between the sonics and the hot wires here that gives you some confidence in the trend. And the sonics, this is just for that very near neutral period. Now the Hutchins and Marusic data is from a longer sample, so you can see their spectra are a bit cleaner than ours, but they were only working from the sonics. So they get a different snapshot of the same flow. Right? And there's an overlap between the, as I said, between the hot wires and the sonics of a small range in Z class. But the thing to point out is, whereas these two are reasonably close in the laboratory boundary layer, so this second peak is between a lambda x plus about 10 to the 4 and 10 to the 5. Out here, we've gone from 10 to the 3 to between 10 to the 5 and 10 to the 6. So the scale separation is increased. You can also make some arguments about k to the minus 5/3 scaling and where you would expect to see that. S plus here is a shear scale proportional to kz. And if you're back into y, okay, it should be z. If you're very close to the wall, your ck is k to the 5/3 times the power spectrum. So if there's 5/3 scaling, you would expect to see a plateau, an extended region here of a constant value. So you don't see that close to the wall in the blue. You do see something like that much further from the wall. Now the red shows you where the dissipation sits in the spectrum, and you can also see that close to the wall, the inertial subrange, something that looks like 5/3 scale, overlaps where the dissipation is, and then at the higher, further from the wall, doesn't overlap so much. I won't have time to go into Pomodoro scaling too much, but it's an interesting question about whether you expect. So a 5/3 scaling would indicate an approach to local isotropy of the flow. And it's an interesting question about whether one would expect to see that in a turbulent boundary layer or not. Or where. Okay, so we've got 15 minutes, so you can make it. No, nothing. So 15 minutes. So let's see if we can just put together some of the more research level questions associated with the surface layer with the picture that Philip put together in terms of statistics and structure in the surface layer. So I talked a little bit about these large scale motions, or very large scale motions, and Philip addressed these yesterday too, so bulges, very long things. He also mentioned the hairpin packet model. So here are the classical pictures from Adrian et al. Showing the development of these hairpin vortices, and there were some beautiful visualizations of these yesterday. And then the velocity, the local instantaneous velocity that should be associated with collections or packets of these hairpins. And sort of also touched on this, the idea, and I showed you with the composite pictures of the time record, that there's an influence of the large scales on the small scales. And you can see that clearly in this figure. So for a portion of one record, we took a low pass of the signal, a temporal low pass filter, and then the red is the high pass signal. And you can see that at this particular height, this is quite close to the wall, Z plus is 10 to the 3, the small scales, the amplitude of the small scales responds to the amplitude of the large scales. So this is a sort of open research question, but you can see it very clearly in the surface layer. Okay, so what kind of structure do you see in the surface layer? And Philip mentioned yesterday there was a question about whether you see these very beautiful symmetric hairpins as the Reynolds number starts to increase or not. And hairpins have yet to really be picked up in the surface layer. You can see these inclined shear layers. So here's a PIV plot from Emmer et al., and this is a smoke visualization. So you can see these bulge-like, not the full bulges that extend to the edge of the boundary layer, but you can see these inclined shear layers and inclined structures close to the wall. So you do see those. This is the slide about the PIV, Morris et al. So I showed you the setup already. Here's an instantaneous field. And if you color code the velocity by in bands, you just bin the velocity, you can see these inclined regions of something close to a uniform momentum or a uniform velocity. And that's what you would expect to see if you had hairpins in the flow, but if you look here, you really can't, you can see some sort of swirling here, but you really can't pick out hairpins in the same way that you saw in the DNS yesterday.
What is special resolution?
Yeah, so that's the question, right? So I'll show you the exact domain in a moment. Still my punchline. So the question is whether you have the appropriate spatial resolution to see them in this figure or not. So here, so this is 5 seconds of the data that we took, and if you use Taylor's hypothesis to put together what the physical extent of the PIV window would be, it would sit here. Okay? So the PIV window was half a meter in height by 2 meters, and then I actually don't have the figure for exactly what the spatial resolution is, but it may be that the window looks small in compared to this long data record, but it may have been too big to resolve hairpins. So it depends on how big those vortex cores would be in the flow. You can look at the instantaneous profile. So this is with no sliding windows, it's just what the instantaneous profile would look like, and then the dashed line is the local mean. And you can see again evidence of what I was showing you before, these regions where the momentum, the velocity, is approximately constant over quite a large distance in the vertical direction. Particularly in this one. This is very interesting sort of shapes that are consistent with those uniform momentums over there. What I wanted to show you here is this modulating effect over a range of more normal distances. So I explained that a couple of slides ago, but you can see that the small scale activity is quite large, modulated by whether the large scale excursion is positive or negative. Okay, so I won't spend too much time on this. This is just a way to quantify that modulation. If you want to see more information, it's in the Mapping et al. Paper. Would draw your attention to the fact that this is the laboratory scale data, and here's the surface layer data. So whatever trend you thought you saw here, in inner scaling, the surface layer data shows you that that's probably not correct, but outer scaling is a little bit better. If you want, I can talk to you about this later. I'm just going to keep going through this slide. The full information is in the map. This actually shows you pictorially the kind of thing that was shown in the previous slide. So if I take the data records from these 8 heights from the synchronously acquired data, and I plot a low pass signal, a high pass signal, and then a band pass in the middle, you see some interesting things. So I've showed you this modulation effect, so thousands here. So this was the exact signal I showed you on that earlier slide. So high, small scale activity during a large scale positive excursion, versa. And if you look across the whole layer, you can see something that's very correlated in time. Okay, so you see this large-scale negative excursion that really is, you see it on the top wire, you see it on the wire closest to the wall. However, if you look at the small-scale activity, you can see that it's suppressed close to the wall, but it's really not so clear what it's doing further. And there's a very complicated relationship between the small scale and the large scale that we just need to cover. But you can also do the same thing by looking at this bandpass signal, and you can see there's a positive excursion here that extends at least some way from the wall, and you can see its effect modulating that signal as well. So this modulation effect occurs across many scales. It's very strongly associated with this very large scale motion, this second peak in the spectrum that I showed you before. And you even see it down to the dissipative scale. So if you look at a large scale negative excursion and a large scale positive excursion, and then you look at the local dissipation, so the dissipation divided by the mean, you can see, we know that the dissipation signal is very intermittent. You can see once again quite strongly influenced by this very large scale. One can look at where that modulation is concentrated in scale space, so which scales are most influenced by this particular large scale that we're looking at here. So here's the full spectrum, composite spectrum in frequency now instead of wavelength. And if you look at the difference in spectrum between positive excursions and negative excursions, you can see that the thing that's most strongly influenced is the near wall peak. And so the small scale activity close to the wall, and this is corresponds to a lambda x plus about 10 to the 3, that's most highly modulated by this very large scale motion. But it's a broadband effect over a range of peaks. One thing I skipped, I just want to get back to here. Typically when you take temporal data, you want to put it into wave number, put it into the spatial domain, and the convective velocity relationship is not clear, so it's usual to use Taylor's hypothesis of frozen turbulence and use the local mean velocity to convert between the temporal and the spatial domain. And usually there are known issues with that, but usually it's not too big of a problem. But if you look at this temporal record here, you can see that the surface layer exacerbates these problems. So clearly between these dashed lines there's something that's correlated all the way through the layer. Okay, there's a large scale negative excursion all the way through the layer. But the difference in local mean velocity is so high in the surface layer that if I converted to the spatial domain up here, I would say that this corresponded to 6 times the bounded thickness, 6 delta, and down here it would be less than 1. So if I were to convert to the spatial domain, I would not necessarily be able to identify that this was something that was coherent across the layer. So the surface layer, this scale separation, this large range of velocities, is something that really highlights some of the things that we can not deal with or not worry too much about lower levels. 2-point correlation. We're very nearly there. Hang on. 4 minutes. So 2-point correlations. If I take the velocity signal at a certain point distance from the wall and I correlate it with a signal at different heights from the wall, I can form this rho u. And if I do that with a point that's close to the wall, so the reference point is 120 degrees from the wall, you see something that's quite familiar from the laboratory reference. So you see this inclined angle. So here we have converted to the spatial domain. You see something very similar to the spatial domain. So you'll see this inclination of the angle of the peaks, and it's somewhere, if you track this peak correlation, it would follow an angle somewhere between 10 and 20 degrees. So that's quite consistent with these inclined shear layer structures I was showing you before. You see something interesting. So this domain fits in this red box. If I now take a reference point further from the wall, so at 4300, you see that whatever's out here doesn't have that information anymore, and it's really correlated without any spatial phase relationship further from the wall. Now, you could say, is this an effect of buoyancy, something that's in the surface layer? But increasingly, as the Reynolds shown that the structure further to the wall is quite different from close to the wall. And that's a high Reynolds number effect. Now this effect is very good from a modeling point of view because Maristic and Hewer have shown that that angle really doesn't change with Reynolds number. So you can get to it by correlating, they correlated the shear stress signal, in red here, with the sonic anemometer signal from the setup I showed you at SFS. And if you do that for these two wires here, and you plot that inclination, apparent inclination angle, these are the surface layer results, and these are the laboratory layer results, the laboratory results. So that inclination angle is essentially Reynolds number invariant, which is very good news for turbulence models where you want to model what's going on close to the wall. So this is really a nice result. So over 3 decades of Reynolds number, that angle is about constant. I showed you those very long structures in the surface layer, about 10 delta. So from this span-wise array of sonic anemometers, Hutchins and Marusic were able to reconstruct, so they used the local mean velocity to reconstruct what the spatial signal would have looked like. And you see, I think it's probably come out a little better on your handout. Hopefully, otherwise I'll improve the resolution. I'll try and improve the resolution for the copy that I'll give you third. The blue here, the dark, is a low speed contour of low instantaneous velocity. And you can see this very long structure. And if you took just one wire, it would have a signal about 6 delta in length. But you can see that it kind of apparently wanders in and out, wanders across this array. So there's a question now about whether that's really a much longer structure, so something that's about half a kilometer in length, or whether this is just several put together and your eye says, well, it's all one structure or not. But either way, you need to consider very long things. So physically, these are half a kilometer plus in length of the surface layer. And you can see the influence of them in the correlations as well. Summary. There you go. You made it. So, I've given you a very broad overview of the planetary boundary layer. There are references that will lead you to where you get more information on that. What I've focused on here is using the near-neutral atmospheric surface